Hello, welcome back to this ongoing course on structure, stereochemistry and reactivity of organic compounds and intermediates, a problem solving approach. Okay. Last time or in the last lecture, we have introduced to you the some phenomena which are known as optical rotatory dispersion and circular dichroism. This is basically associated with chiral molecules, and the outcome of this phenomena have been applied successfully to establish various aspects of organic molecule, like the conformation, the configuration, whatever may be the case. Okay. Now, just to remind you, we started with plain polarized light. That was when the stereochemistry subject is introduced at whatever at the beginners level. We were told that there is a special kind of light which is called plain polarized light, where the oscillations are taking place, oscillations of the electric vector and the magnetic vector. They are taking place in a particular plane, okay, as the light propagates. So, that is plain polarized light, and then I told you that this is also known as linearly polarized light. And linear polarized light is basically a combination of both right and left circularly polarized light. So, basically you have RCP plus left circularly polarized light, LCP. Now, this is because this is circular, right circularly polarized light is basically the when light proceeds, the oscillations take place in a helical fashion. If it is a right handed helical fashion, then that will be right circularly polarized light. If it is a left handed propagation, then that will be a left circularly polarized light. Okay. So, it is a combination of the two, but the helix a helix is inherently chiral. So, basically these are two chiral entities, right circularly polarized light and left circularly polarized light. So, when it interacts with a chiral molecule, so their interaction, that means the interaction of the chiral molecule with RCP or LCP will be different. Now, the question is what type of interaction? The interaction is nothing but the there are two kinds. One is the regarding the velocity of the two components of light, velocity, which is connected with we know that that is connected to the refractive index. Okay. So, when light travels through a chiral object, light like this linearly polarized light, because its two components RCP and LCP. So, the two components will have different refractive index. Okay. So, that is one aspect, and this is what is called birefringence, circular birefringence. Okay. Circular birefringence, that means you are having different refractive indices. Okay. And the other phenomena that will happen is basically that the kind of absorption, because whenever light passes through a medium, there will be absorption. Now, since it is a mixture of two components, so the question is whether both the components are absorbed at equal extent. That will happen only if the light is passing through a symmetric medium. If it is passing through a disymmetric medium, that means a chiral medium, then what happens? The two lights are absorbed to different extents, and that gives rise to a phenomena which is called circular dichroism. So, there are two kinds of effects that are seen when a linearly polarized light passes through a chiral medium, that you have circular birefringence, that means different refractive index that leads to different velocities, and the other is the different absorption, extent of absorption. So, that is connected to circular dichroism. Okay. So, today we will be seeing the optical, we will be discussing the optical rotatory dispersion. Now, what is optical rotatory dispersion? This is basically the kind of observation that you make when when you plot the optical rotation of a chiral molecule with variation of the lambda, the wavelength. Okay. Basically, we know that the specific rotation of a compound is actually measured. There is a reference temperature as well as a reference wavelength. Why that is so? Because the rotation is dependent upon the wavelength of the light as well as the temperature. Okay. Now, if you fix the temperature, do not vary the temperature, if you vary the wavelength of light, then what happens? The amount of rotation will change. Okay. Now, the question is change in which direction, okay. But whatever changes are taking place, that is what is called the ORD or optical rotatory dispersion. That is the change, it is actually basically showing the change of optical rotation against wavelength of light. Okay. Now, we know that the way this standard wavelength of light at which the specific rotation is measured, that is the sodium D light, that is 589 nanometer. Okay. So, what happens that if you have a, if you try to plot a graph where this is lambda and this is the lambda increasing in that direction and this is the alpha, suppose. Okay. Alpha in the sense that it could be molar rotation or it could be specific rotation. So, it is rotation, but it is, you have to fix the, either it is specific rotation or it could be a molar rotation. Okay. So, if you plot that, then what happens that suppose the you started at 589 and the rotation is this is the positive side and this is the negative side. So, that is the 0 line. Okay. So, the rotation will change. Okay. Now, what happens usually, what happens, this rotation changes and it increases like this, okay. Or in some cases the rotation decreases like this. Okay. And a third possibility is that there may be crossover. That means, some rotation you start at 589 as a levorotatory, but as you lower the wavelength, it ultimately crosses the 0 line and becomes dextrorotatory. I think I reminded you that if a question is asked that can a levorotatory compound show positive rotation, you say yes, it is possible. It is hard to predict which one will do that, but it is possible by changing the wavelength of light. Okay. So, this is your this type of graph or curve that you get is what is called plane curve, where the rotation continuously increases or rotation continuously decreases. Okay. It is not a mixture of increase and decrease. This is what is a plane curve. However, this plane curve you will get when your wavelength of light falls outside the region in which region of wavelength at which the compound absorbs the light, okay, because the compound has a chromophore and the chromophore will absorb the light. Okay. So, if you are measuring the rotation at wavelength region which is away from the absorption wavelength for the compound, then you see the plane curve. Okay. On the other hand, if you are measuring the wavelength, if you are measuring the rotation against wavelength which falls within the absorption window, then what happens? Then what you get is what is called anomalous curve. Anomalous curve is that there could be several types, but anomalous curves means now you will not have a continuous increase or decrease. What will happen that there will be a mixture of increase and decrease, okay, or it could be decrease and increase, both are possible. Okay. So, what happens that you get a graph like a curve like this, you get a curve like this. Here it is rotation has increased and then reached a maxima and then drops rapidly and becomes 0 at this at a particular wavelength and then goes down and reaches a minima and then goes up. Okay. So, this is what is called an anomalous curve. So, optical rotatory dispersion is basically can show a plane curve or it can also show an anomalous curve. Only remember that anomalous curve is obtained when you have a wavelength region which is within the absorption region of wavelength for that compound. Okay. And plane curve you will get if you are measuring outside the region of absorption. Okay. So, this is one possibility. The other one could be that there could be first decrease, you get a minima, then you get a maxima like this. Okay. Now, when you get this type of anomalous behavior and you get an anomalous curve, we say that the compound is exhibiting a cotton effect. Okay. The cotton effect is nothing but generation of an anomalous curve or a behavior of a compound which shows an anomalous curve in the absorption region, and the curve could be of two types, that it is a mixture of maxima and minima, but the question is which comes first as you lower the wavelength. If you lower the wavelength, then if the maxima comes first followed by the minima, that is, we say that the compound is showing positive cotton effect, and on the other hand, if the minima comes first like this, the minima is first as you lower the wavelength and then the maxima, then we call that the compound is exhibiting negative cotton effect. Okay. Now, this sign of cotton effect is very important, because by measuring the sign of cotton effect, you can equate the sign with a particular conformation or configuration of a molecule. Okay. So, today we are going to discuss that. First, so that is clear what is anomalous curve and what is plane curve and what is your cotton effect. Okay. So, that we know. Now, let us proceed further. Okay. Now, what is the use of plane curve? That is the first question. What is the use of a plane curve? Now, the plane curve is used mainly to establish the chiral nature of a molecule. Not all molecules, but there are some molecules which has a very minimal rotation at the sodium D light wavelength. Okay. So, if you have a molecule which shows very little or minimal rotation at 589 nanometer, now you might think, or the experimentalist who is measuring the rotation, he or she might think that it is not a chiral compound. It is or if it is a chiral compound, it is a mixture, it is a racemic mixture, but it is not an it does not have any it is a racemic mixture, that is one possibility, or it is an achiral compound, both are possible, right, which where the rotation is basically within the error limit. So, you might get say 0.5 degree rotation. Now, whether it is due to any experimental error or is it due to the fact, the very fact, the nature of the compound which is showing very low rotation at 589 nm. Now, how to distinguish that you are starting with a racemic mixture or an achiral compound, or your compound is really a chiral compound with a one enantiomeric form, or at least which is having more than 50%, which is present in more than 50%. Okay. So, let us see, let us take a very defined situation where there are possibilities that if you have a minimal rotation at this point, suppose the rotation is at this point. So, very close to 0. So, what are the possibilities? That it could be a racemic mixture, oh sorry, it is not visible. So, it could be the possibilities is that it could be a racemic mixture, or it could be an achiral, or it could be an enantiomer having very low rotation at 589 nm. Okay. Now, how to distinguish between these three scenarios? So, what you do, actually it is not possible to distinguish between racemic and achiral, because as you lower the wavelength now, if it is racemic, both the enantiomers will behave just in opposite way. Opposite means if one tries to increase the rotation, the other will try to decrease the rotation, but to equal extent. So, the overall rotation remains the same. Actually, in racemic mixture it should be 0 or close to 0. So, what will happen if it is racemic? It will not change, it will just go like this. Okay. If it is an achiral, that is the same thing that will happen. Okay. But if you from the very beginning you know that yes, I have a chiral molecule, but I am not sure whether it is a racemic mixture or it is a where it is a mixture where one of the enantiomer is predominating. Okay. Such type of scenario. So, then what will happen if it is a particular enantiomer, or if an enantiomer is predominating in the mixture, then what will happen, the rotation will now change with wavelength, and you generate a plane curve. Okay. So, you understood that for compounds with very minimal rotation at 589 nm, the standard wavelength that we express the specific rotation, if it is close to 0, then you run the risk that either handling a racemic mixture or handling a mixture where one enantiomer is more, but the rotation at that particular wavelength is very low. Okay. So, in order to distinguish that, you have to lower the wavelength and see the kind of curve that you get. If it changes with wavelength, increases or decreases, then you are definitely having a mixture where one enantiomer predominates, or you might be having one particular enantiomer which is almost pure. Okay. So, these are possibilities. So, you can distinguish between racemic mixture and a mixture where one form predominates. Okay. We are assuming that already from the very beginning we discount this achiral nature, because suppose we know the structure already. So, we know that this molecule is chiral or not. If you know the structure, you can make out whether it is chiral or not. Okay. So, we are discounting the achiral nature, because as I said, the racemic and achiral, it is not possible to distinguish between the in terms of this ORD. In that case, if you want to distinguish, you have to try to separate the racemic mixture into two, whereas achiral compound are basically it is one entity. So, that is one of the that is the use of the plane curve. The more interesting one is, so from plane curve what we know, that plane curve says that that first of all a levorotatory or a dextrorotatory compound can change sign as you lower the wavelength, that is one possibility. And the other one is the use of plane curve is to distinguish between a racemic mixture and a mixture where one form predominates. Okay. Now, let us come to this anomalous curve, that is what is more interesting, and that is more that is applied or that has wider application in understanding the conformation and configuration of molecules. Okay. So, now there are certain empirical rules that were developed in the early 60s or late 50s, some empirical rules to predict the sign of cotton effect based on the configuration or conformation of a molecule. Okay. So, one such empirical rule is what is called axial haloketone rule. Axial haloketone rule. Okay. To be specific, it is called two-axial haloketone rule. Now, what it says, that if you have a cyclohexane system, if you have a cyclohexane system, cyclohexanone system, sorry, if you have a cyclohexanone system, that means there is a carbonyl group somewhere in the molecule. Okay. Suppose here I put a carbonyl, and now if you halogenate, if you do alpha halogenation, because carbonyls are susceptible to alpha halogenation, and if you do monohalogenation. So, if you do monohalogenation, then what will happen? The halogen can assume an axial orientation, or it can assume an equatorial orientation. Both are possible, right? Now, sorry. You know that because of this repulsion between this electronegative oxygen and the bromine, electrostatic repulsion. So, the halogen tries to occupy the axial orientation, and this can be verified. The axial or the equatorial nature of an halogen can be verified by taking the by measuring the spectroscopy, especially like IR spectroscopy. You look at the carbonyl stretching frequency of this this hexanone system, cyclohexanone system. Okay. So, basically by spectroscopic means, if you do halogenation, you can check whether the halogen is occupying axial or equatorial orientation. Okay. Now, this rule, the axial haloketone rule, says that this rule is applicable to systems where the halogen is occupying an axial orientation, number 1. Okay. Then, if you want to stop the mobility of this molecule, that means the flexibility of the molecule. So, you know that you have to lock the conformation. So, by putting a bulky group like T-butyl. Okay. So, I lock this conformation by putting the T-butyl group. Okay. Now, when I suppose I started with this cyclohexanone 4 tertiary butyl cyclohexanone, okay, then I do halogenation. Now, halogen can take place here, or there is a possibility that you can have the halogen at this position. Both are axial. So, by spectroscopic means you know that the bromine is axial, say halogen, I put bromine, say any halogen, but not fluorine. Okay. This is only applicable to chlorine, bromine and iodine, the axial haloketone rule. Okay. Now, basically what happens that these two molecules will exhibit different Cotton effect, will exhibit different sign of Cotton effect. Okay. So, one will show positive Cotton effect, another will show negative Cotton effect. Now, which one will show positive and which one will show negative? The rule says, that empirical rule says that if you look from the side of the carbonyl and look into the inside the cyclohexane system or look into the cyclohexane system, then what will happen that your halogen will either be to your left hand side or to your right hand side. Okay. That will happen if I stand here and look. So, it looks that the hydrogen, if I stand here and look at this system, so the halogen will be towards my left and this halogen will be towards my right. Okay. So, depending on this right left, the sign of Cotton effect will depend. That is one aspect. The other important aspect is that in a cyclohexane chair form, you have some carbons which are called head of the chair, like this one and this one. So, these are the head of the chair. Okay. And some are which are called the leg of the chair, like this. Okay. So, these are pointing downwards and the head of the chairs are pointing upwards. Okay. When you look into the cyclohexanone system, looking from the side of the carbonyl, you have to make sure that the carbonyl carbon is occupying the head of a chair. Okay. So, to apply this rule, first make sure that the carbonyl is occupying the head of a chair and then you look from the side of the carbonyl and look into the cyclohexane system, and then if you see that the halogen is towards your left, then it will show negative Cotton effect and this will show positive Cotton effect. Okay. Now, you have to so this is entirely an empirical rule, but there are some rationale behind this. It appears that the sign of the Cotton effect is solely dependent on the nature of the presence of X. Okay. Even if you have other substituents somewhere, but they will not part out the sign of the Cotton effect as dictated by the axial halogen. Okay. This is because the halogen is highly polarizable, and because of the high polarizability, the halogen actually overweighs the contribution of any other substituent to the sign of the Cotton effect. Okay. So, basically halogen determines, it predominates in dictating the sign of the Cotton effect because of the high polarizability. Okay. And we know that fluorine is least polarizable. So, you cannot so fluorine is not applicable here, it is only chlorine, bromine, iodine. Okay. So, that is the rule. Now, let us try to apply it to solve some problems. Okay. Now, what are the problems? The problems is basically to determine the the geometry of a molecule. Determine the geometry means geometry can be conformational geometry or it could be configurational geometry. Okay. So, let us start with a molecule, the determination of absolute configuration of, let me see, the problem is like this, that determination of absolute configuration of a molecule minus, let me see what is the problem, minus trans 1 decalone, okay, minus trans 1 decalone. Okay. Now, this is applicable, this again just to remind you that the Cotton effect that we are measuring for the cyclohexanone system, it shows the Cotton effect definitely near the absorption region, as I told you, that is where all these effects come, and carbonyl has an absorption which is corresponding to the n pi star transition. So, it will be very close to the 280, 300, that type of nanometer range. Okay. So, minus trans 1 decalone, we want to determine the absolute configuration. Okay. Now, what is done, because the experiment that was done, that first you do alpha bromination, monobromination. Okay. Usually monobrominations, if you want to have monobrominations of carbonyl, you know that it has to be acid catalyzed. Okay. So, bromine, so you get monobromo. So, what you will get trans, now you will get 2 bromo, I will show you the structure, at least the planar structure, 2 bromo 1 decalone, okay, trans, and this one, by the way, the bromo derivative that was obtained is positive, has positive rotation. Okay. So, you started with a particular compound trans decalone which is minus, and you want to levorotatory. So, you want to determine the absolute configuration of this. So, once you fix the absolute configuration of this, you know what is the absolute configuration of the plus compound also. Okay. Now, the way to do it, basically the experiment that was done, that you brominate it to the 2 bromo 1 decalone and then check the Cotton effect. Okay. Now, what is the Cotton effect? It shows, that is experimental, it shows strong positive Cotton effect. Okay. So, that is the result, experimental result. Now, how to how does it help to arriving at the configuration? Okay. So, first what you do, you write the trans 1 decalone. Okay. So, trans 1 decalone means this is your decalene system, and if it is your 1 position 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So, suppose this is the carbonyl and this is your, so it is trans. So, you make it trans, the hydrogen, 1 hydrogen beta, 1 hydrogen alpha. So, that is one possibility, and the other possibility is the mirror image of this. Okay. So, let me erase this. We do not know whether this is minus, whether this is the minus form or the minus form is the mirror image. So, if it is the minus form, the mirror image is plus. If this is the plus form, the mirror image is minus. Okay. So, we want to determine the absolute configuration. Absolute means you really know the RS configuration at the stereogenic center. Okay. So, the other possibility is the mirror image. So, any one of these could be the absolute configuration or represent the minus trans 1 decalone. Okay. Now, let us draw this in the chair form. Okay. So, if we draw it in the chair form, so this is the scenario. Okay. So, this is your carbonyl, this is your, so now this is not the, so let me just change this a little bit, because to show this in this form, it will be alpha and that will be beta. That is also not a problem, is anything you can do, but since I have drawn the chair like this, so I make this alpha and that beta. Okay. So, this is your this is corresponding to this one, and on bromination you get alpha bromination and the bromine was axial as determined by spectroscopic means. So, this is the bromo derivative and the other bromo derivative will be carbonyl on this side, the hydrogen, and this is the bromo. Okay. So, these are the two. Now, you predict the as per the axial haloketone rule, you try to predict the your sign of cotton effect. If this is the structure, just a word of caution, first make sure that the carbonyl is occupying the head of a chair. Yes, this is occupying the head, this is the head of a chair. So, this is the right way to visualize. Okay. So, you visualize along the carbonyl and as you see this bromine comes towards your left. So, this should show negative cotton effect, and if this is the structure, if you see again this is the head of the chair. So, you look through the carbonyl and into the cyclohexane system and the bromine is towards your right, okay, the axial bromine. So, that will show positive cotton effect. So, that means your minus trans 1 decalone, the correct structure, 3-dimensional structure is this, and if you assign R S, so you can actually now tell which one is R and which one is S. Okay. So, the absolute configuration at these two positions are now clearly demonstrated on the basis of the sign of the cotton effect, applying this to axial haloketone rule. Okay. Now, we will take another example. Let us see determination of conformation of a cyclohexane polycyclic compound containing several cyclohexane rings, okay, like a steroid. Okay. Now, the example that is, so first one was configuration, now we are talking about conformation. The example that I will be talking about is an interesting example which showed that the A ring of a steroid, substituted steroid system can exist in the boat conformation or in the skew boat conformation. Okay. So, let us see what is that that type of compound which we are talking about. See, this is the compound. This is the typical steroid skeleton, that parhydrophenanthrin and followed by a cyclopentane, okay, fused, and that is what is the typical structure of a steroid. Okay. Now, steroids have also methyl here and methyl here. Okay. These are beta methyls, and the substituted steroid that we are talking about is a particular one, is this one. So, this molecule is basically a ketone that you need, because to check the ORD, that to get an anomalous curve you need a chromophore. Okay. So, the examples that we will be presenting to you are all basically based on carbonyl as a chromophore. Okay. So, this is the molecule. So, these are 3 rings here, and the way you draw this molecule, remember when you do not show any stereochemistry, that means A ring will look like this, and this is a trans ring junction. So, that will also be this one, okay, carbonyl, and this is your methyl, this is the methyl already present, and this is a hydrogen, and then you have the rest of the molecule, okay, the rest of the system like this. Now, let us consider another problem where basically we have to find out the preferred conformation of a particular compound, namely a decalin derivative whose absolute configuration is known. Okay. The compound is plus cis 10 methyl 2 decalone. Okay. And as I said that its absolute configuration is known. So, I will write the actual structure. in planar form. So, this is the absolute configuration, or this representation gives you the absolute configuration of this molecule. This is the plus molecule representing cis-10 methyl 2-decalone. Okay. So, this is the molecule, the numbering goes like this. This is your 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. Okay. Now, because it contains a cis-decalene system, as you can see, it contains a cis-decalene system. So, it can exist in two conformations, okay, because cis-decalene system we know can be flipped. Okay. So, one conformation I write, and that is this one. This is the two chair forms. So, let us name these cyclohexane rings. This is the A ring, this is the B ring. Okay. So, this is my A ring and this is the B ring. Okay. Now, the question is, where is the carbonyl? The carbonyl is, so this is your number 1, this is your number 2, 3, 4, 5, 6, 7, 8, 9 and 10. Okay. So, the carbonyl is here at the 2 position, and you have a methyl at 10 position. This is your methyl, and you have a hydrogen which is also beta. The methyl is beta as well as the hydrogen, that gives a cis ring junction, cis-decalene system. So, this is one of the conformation of this molecule. Okay. And there is another conformation I can write, because this can be flipped. So, if you flip this, molecule, so this will be the representation of the B ring, direct representation of B ring after flipping. Okay. And when I discussed the conformation of cis-decalene, I told you that there is a problem here of representation of the A ring, because A ring's projection looks like a plain hexagon, but actually it is in the form of a chair. Okay. So, here this is the methyl and this is the hydrogen. So, in order to, so this is my A ring. In order to represent both the rings in the chair form, so you give it a turn of 60 degree. 60 degree if you turn in an anti-clockwise direction. So, it will take this form, and the A ring now can be represented as a perfect chair. Okay. Where is your methyl? The methyl is here, this is the hydrogen. Where is the carbonyl? The carbonyl is at this position. You put the numbering to make it all clarified. So, this is 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. Okay. So, these are the two conformations. Okay. By the way, this is what is called a steroidal conformation. This is what is called a steroidal conformation, and this is, by the way, is called non-steroidal conformation. Okay. The genesis of such a name is basically there are some steroids which has say steroid has 4 rings. The first ring is called A ring, if I draw a steroid. So, steroid has this parhydrophenanthrene system as well as a cyclopentane. So, this is A ring, B ring, C ring and D ring. Okay. Some steroids have this as a cis ring junction and this as a trans ring junction. So, BC is trans, AB is cis. Now, in that case what happens that you can represent the conformation of this only in terms of this form, okay, because of the reason that you try it yourself, that if you try to start from here to represent this steroidal molecule, you will see that I cannot construct the B and the C ring, simply because the ring junction bonds become diaxial, and you know the diaxial bonds cannot be connected, that we know. So, that is why the steroids being present in this form, this is called the steroidal conformation, and this is what is the non-steroid. So, these type of steroids cannot acquire this type of conformation, simply because you cannot draw the C ring, because BC ring is trans ring junction which is rigid, and that makes the whole molecule, steroid molecule, rigid. Okay. So, let us now try to see whether this system, this is not a steroid, this is a decalene system. So, it has the option of adapting both the conformations or one of the conformations. It can be conformationally biased. Okay. So, in order to do that, because it is a cyclohexanone derivative, so you can take the Cotton effect, you can measure the Cotton effect, and what was the experimental observed Cotton effect? Experimental, that it shows negative Cotton effect. Okay. Negative Cotton effect. Now, let us try to draw the octane projection to see which one gives negative Cotton effect. Okay. Now, you know that when I draw the octane projection, the carbonyl has to occupy the head of a chair. The way I look along the oxygen carbon bond, that I look from this, but I have to make sure that the oxygen is occupying the head of a chair. Now, in many cases what happened, the oxygen, the carbonyl is not occupying, this is not the oxygen, the carbon is occupying the head of a chair. Okay. So, in many cases the carbonyl carbon may occupy the leg of a chair, like here. In this form, the carbonyl carbon is occupying the leg of a chair. However, in the steroidal conformation, it is occupying the head of a chair. So, you can see from this direction, and whatever you see, you just draw the projection. You do not have to change anything, the right or left, up and down, you do not have to change anything. Okay. So, if I now start drawing the octane projection, so this is my 2 in the middle, okay, that contains the carbonyl, and then 1 is on my right side, and 3 is my on the left side. Okay. And then 1 goes up, that goes to 9, and 9 comes back to 10, and then 10 is connected to 4. So, these are the 6 atoms, the projection of the 6 carbon atoms of the E ring. Okay. Now, you have to you know that the axes are basically going through these 3 carbons and through this. Okay. Let me put another color. Okay. So, this is my axis, and this is remember, this is actually the rear, we are drawing the projection of the rear octant. Okay. All the groups are occupying the rear octant. Okay. Now, let us, we have to complete the B ring. Okay. In order to complete the B ring, we have to find out, see, B ring is constructed via via the 10 and the 9. Okay. So, at 10 carbon atom, this methyl is equatorial with respect to the A ring. Okay. Is equatorial with respect to the A ring, and 5 C5 is axial with respect to the A ring. Okay. Remember that in a cyclohexane, when we drew the cyclohexane like this, all the 6 atoms are here. If the axis goes like this, then the axial goes down and the equatorial goes up. I told you that always be comfortable in writing the octane projection of a cyclohexanone system. So, this is how the axial equatorial are disposed. No? This is equatorial, that is axial, this is equatorial, that is axial. So, based on this diagram, now you can complete the full projection of this molecule. So, 10 is connected, methyl is equatorial to 10. So, this is methyl, okay, and the 5 carbon goes down. So, this is your 5 carbon, and on 9 this is actually equatorial with respect to the A ring. Okay. So, this is 5 is connected to 9 is connected to 8. So, now you have 4 atom projection of the B ring, 8 has a projection here, 9, 10, 5. Okay. Once you have the projection of 4 atoms of a 6 membered ring, you can complete the full projection. That what I am saying, that now we have 4 points like this. This is 8, this is 9, this is 10, this is 5. So, the complete projection will be something like this. It will take a projection like this type of rectangle. If you have 4 points which are going like this, then your projection complete projection will be something like this. Okay. So, your duty is to first to just find the projection of 4 atoms, and then you can just complete without seeing anything. You do not have to see any other drawings, you just complete it. 8 is here. So, 8 is connected to 7 and 7 is connected to 6, 6 is connected to 5. Okay. So, this is the complete projection of the steroidal conformation. Okay. The steroidal conformation, let us draw the projection of the non-steroidal conformation. Okay. Non-steroidal, we have to look through the oxygen carbon axis, but here the problem is the oxygen, the carbonyl carbon is occupying the leg of a chair. So, whatever you see right and left, you just change. So, C1 appears to be on the right side, but actually when you turn it upside down to make the carbonyl occupying the head of a chair, then it will be just the opposite. The one will be towards your left. Without turning it, as I said, you do not have to do anything, you just think that yes, I am looking, or you consider these points that I am looking from the oxygen carbon bond where the carbon is occupying the leg of a chair. So, whatever is to my right, that will become left. Okay. So, it is now easy, this is number 2, that is the carbonyl. So, on the right side it will be 3, on the left side it will be 1. Okay. And then 3 is connected to 4, 4 is connected to 10, 10 is connected to 9 and 9 is connected to 1. So, this is the projection of the A ring. Okay. Now, you have to complete the projection of B ring. At 10, the methyl is, see, because the methyl is this projection, remember this projection is for the A ring. So, when you try to draw the projection of methyl, you have to consider what is the status of methyl with respect to the A ring. So, with respect to the A ring, methyl is axial, and we know the axial goes down. Okay. So, this is your methyl, it goes down, and what is the other point of connection? This is the equatorial, the 5 carbon is actually occupying the equatorial. This is the equatorial bond, 10 5 is an equatorial bond with respect to A. So, this will be your 5. Okay. And now, you have 9, this bond is what? This is axial, the 8, the 9 8 bond is axial with respect to the A ring. So, axial goes to the top, okay, to the upside. So, that is your 8. So, now it is easy to complete because you have 4 points already. So, this will be 7, sorry, let me erase this structure. So, that will be your 7 and this will be your 6 and this is the octane projection. Remember, this is your the 2 axis. Okay. This is the upper right, this is the upper left, this is the lower left and this is the lower right. Okay. And you know the sign of Cotton effect, this gives minus, this produces plus, this gives minus and that produces plus. So, here we are seeing more of this. If 9 crosses out the 4, contribution of 4, but still you have 8 7 6. Okay. So, this conformation gives negative Cotton effect, and this conformation on the other hand, if 4 crosses out 9, you still have 8 and 7. So, this gives you positive Cotton effect. Okay. And the experimental result, I already told you, the experimental result was that it showed negative Cotton effect. And so, the correct conformation of cis 10 plus cis 10 methyl 2 decalone is the steroidal one. Okay. So, that is the problem all about, and we have learned how to draw the octane projection, okay, octane projection of decalene molecules written in several different forms, different conformations. Okay. We will do some more problems later on, but for the time being let us call it a day, and so thank you, see you next time.